Okay, so in this video, we're just following up on the last video where we derived in great detail the C3v character table. And so we just wanted to finish up by checking and deriving how all these functions transform. So we just pulled up the character table. We derived this whole component. In the last video, I showed you how the function z can transform. But I'm going to start by drawing our favorite C3v example molecule. You could use any molecule you want, but I like to use something easy like ammonia. And I'm going to draw the principal rotation axis, which is right here. Remember, there's a C3 there, but we always call our principal rotation axis as Z. And so we can then define our X and our Y axes. Our X and our Y axes can be, and I'm just going to erase this part a little bit and make it a little clearer here. So I'm just going to draw that portion of the z vector. We know it goes all the way down that axis, and we can define our x and y wherever we want. It's easiest if we define our x or a y along one of the bonds. So I'm just going to define the x vector as going that way. Obviously, it has to be perpendicular to the z. And then the y is going to be coming out towards us, coming out of the plane of the presentation. And of course, they're all 90 degrees to one another. So it doesn't really matter how you define those. They have to be 90 degrees, but the z has to be with respect to the principal rotation axis. So in the last video at the end, we derived the function z and showed that it did transform as the A1 function. Let's go next and do the RZ function. So what is RZ? RZ is actually the act of, it's a rotation vector. So it's actually what I wrote in red here, this little arrow. So maybe I'll put it in green now. But it's this green arrow and it's RZ. So it's a vector that's wrapping around the pole of the z-axis. And so what we can do now is think about what happens when we take the RZ vector and we transform it with all the different operations. So, or one operation in each class. We can choose any operation. The only operation in the identity class is identity. So we take RZ and we do an identity on it. What happens? We just get back the same thing. That's the definition of identity. So there's going to be a 1-by-1 matrix that gets us from RZ to RZ. That's just the matrix with the 1. We take the trace or the diagonal, the character. It's another word for trace. That's where character table comes from. Just summing up all the diagonal elements. There's only one element here. It's a diagonal. So the character for the identity operation is equal to 1. Okay? And so let's now do C3. C3 is a little bit more exciting. And so we have to think about, okay, let's go back to green here, and we have our little RZ. And now what are we going to do? RZ is defined as a clockwise rotation wrapping around the Z pole, Z axis. And what are we doing? We're doing a C3 on this. That's what we're asked to do. So that's going to rotate this by 120 degrees. Remember, rotation is 360 degrees divided by n, 360 degrees divided by 3 is 120 degrees. We're doing a 120-degree rotation clockwise. So that's just going to take this vector and it's just going to change its position a little bit. But fundamentally, the tail maybe goes 120 degrees, so it goes over there, and the head maybe goes 120 degrees, so it goes over there. But fundamentally, this is still describing the same thing. It's a clockwise rotation going the same direction. We went from clockwise to clockwise. So this actually doesn't change anything. So RZ went to RZ, and again, the same 1-by-1 matrix describes this just of 1. And so the character chi of the C3 operation, we could also do this for C3-2, right, is going to be 1. You can imagine if you did C3-2, that's the 240-degree rotation, the other operation in the C3 class. that's just going to rotate this vector here, even more. So it would look maybe something like that, but it's still the same thing. It's still RZ. It's a clockwise rotation. All right. Now our last one is the mirror planes, right? So the mirror planes, we can choose any mirror plane in the molecule. Let's redraw our nitrogen molecule so we can see here. And if we draw this same z-axis with our same RZ vector wrapping across the pole of the z vector, and now if in blue we draw one of our mirror planes. So I'm drawing the mirror plane that is interconverting these two hydrogens. It's cutting through the nitrogens and the hydrogens, and it contains the z-axis. But what's going to happen here? Something a little bit different. So if I think about now my z vector, my RZ, draw it a little bit bigger here so we can see, and I think about where my mirror plane is in blue. Let's go blue here. It is cutting right through here. And so what that does is it flips. It takes this part of the vector and flips it. That part of the vector is looking at itself in the mirror. So apologies for the different arrows. The red arrow is just showing you how this is flipping. But this head of the arrow is looking into the mirror, so it sees itself going that way now. And this tail is looking to the mirror, and it sees itself going that way. And lo and behold, we went from one direction to now the other direction. And if we change directions of the vector, what does that mean mathematically? We have a negative sign, right? So now we can write down that a sigma v, and if you did it with any of these other mirror planes, you get the same answer. Those mirror planes are going to cut through the vector, and that cutting through is what causes the change in the direction. So sigma v hat is going to take RZ not to RZ, but to negative RZ. And so now the 1-by-1 matrix that describes this is actually a -1. And so that gets us negative RZ. And so our character of the vertical mirror plane is actually -1. So our vector in the end is, what is it? It's 1, 1, -1. So we got 1, 1, -1, and that is A2. And so RZ transforms as A2. So that's a way to check how RZ transforms. You could also test RZ, not knowing what the A2 vector was, and that would be a way to derive these numbers. So that's how this works. So let's now do, as a final thing, we just need to test these other linear functions. So we're going to do x and y. Rx and Ry behave very similarly. And then for fun, we'll look at something like z squared, just so you can see how that works. So if we go back here, and now let's test x and see what happens. So again, we have to draw our nitrogen molecule just as to help us visualize things. And remember, we have our z, we have our x is how we defined it there, and we have our y sticking out of the presentation, coming at us. So what happens? We take an x, and what are we doing? We're doing an identity first. So well, what does that do? X goes to x, fine. That's going to be, it looks like a character of 1 is appearing to be, right? Matrix is going to be 1. And if we looked at y, well, identity would do the same thing. Okay, so no problems there. But now we go to C3. And we go to C3, and what's going to happen? X is going to turn, if we have an X vector, so I'll write it in maybe blue. There's our X vector, and we're doing a 120-degree rotation. So the X vector, it doesn't really matter if you do it clockwise or anti-clockwise. Technically, the definition is clockwise, but for drawing it, it doesn't really matter. So that's going to take 120 degrees. So that's going to go past, if I go this way, 90 degrees would be to the y. So it's going to go 30 degrees past the y. And so x is going to be going into some diagonal. It's not going straight into y. It's not going to negative x. That'd be 180 degrees. It's going into, some trigonometry, ax plus by, where a and b are some trigonometric values. What are those values? Well, it gets into trigonometry, so it's useful to know, you can derive it, but it's useful to know this rotation function. And the rotation function says that basically it's going to go by cosine of theta. So theta here is 120 degrees. And we're going to have cosine theta on this diagonal. And it's going to be sine 120 and negative sine 120. And so that's how it's going to transform. Okay? So what this tells you that x doesn't go in x doesn't go in y, x goes in a combination of x and y. And guess what? Y is going to do the same sort of thing. Okay? And so the issue here is that x and y are dependent upon each other. And so what that means is that they transform together. You can't separate them. And so we have to treat this as a 2x2 matrix. And mathematically, because we have to treat the C3 operation, the C3 class, as a 2x2 matrix, we also have to treat the identity as a 2x2 matrix. So for the identity, we know x goes to x, y goes to y. And so the 2x2 matrix is going to be the identity matrix. 1's across the diagonal, 0's on the off diagonal. That gets us, it takes a 2x1 matrix, x of y and y, goes into x of y. And what we do is we take the trace of this, right, sum across the diagonals, 1 plus 1 equals 2. And that is going to be the character of E. So we got a 2 there. Now here we do the same thing. We take the trace, the sum of the diagonals. And from trigonometry, you might remember that cosine of 120 equals negative 1/2. And so what you get here is cosine 120 plus cosine 120, which equals negative 1/2 plus negative 1/2, which equals negative 1. And that's going to be your character of your C3. Last one is your reflections. So again, we're going to just draw our favorite nitrogen molecule here. And now we're going to draw our x, y, and our z's. Very important to do that when we're considering how all these vectors transform. And we're going to draw our mirror plane. We'll do green. So we choose the easiest mirror plane to draw, which is this one. Again, that interconverts these hydrogens and contains the x vector. So if it contains the x vector, it contains the z vector as well. But that means, so for sigma v hat, x is going to go to x. If you have a vector in a mirror plane, it's not going to change. You can't look at itself in the mirror. It's in the mirror. It's in the mirror. Nothing happens. Y is looking at itself in the mirror. Y is going to flip back to negative y, right? Because it's looking at itself in the mirror. There's y. It looked at itself in the mirror to get negative y. So what does that mean? Well, again, we have to keep this as a 2x2 matrix. So we're going to get a matrix that looks like this. 1 and negative 1 on the diagonal. Because x goes to x and y goes to negative y. That's what our function does. We take the trace of that matrix, 1 plus negative 1. equals 0. So chi, the character of sigma v, is equal to 0. And lo and behold, what do we get? We got character 2 for identity, character of -1 for C3 class, and a character of 0 for the sigma v class. So in essence, we proved right now that the functions x and y, they transform together. That's why we have these parentheses here. That's what it means. They transform together. They're stuck together. They have to go together. And they both together transform. It's a two-dimensional thing. Transform together as E, which is the vector 2, -1, 0. So we derived that vector 2, -1, 0. And we prove that x and y have that symmetry. Okay? You could do a very similar thing with Rx and Ry. I just wanted to show you how a quadratic works. Maybe not the best example on this character table, but we'll work through it, and so you can see what happens. And then in other videos, we'll do other character tables that might show this a little bit more clearly. But just really quickly, how a quadratic would work. So function z squared, it's quite easy. We would just think of, what is the components of z squared? Well, it's z times z. So the function identity, what would that do to z? Well, it takes z to z, and then we have another z, takes z to z, and so one z went to z, the other z went to z, and what do we get then? Well, we get z squared. And all of these, if you remember from the previous video, z always goes to z, so it's always going to just be equal to z squared. But if you work on it for some of these other math, like xz, okay, or yz, because z is basically 1, that's why x times z and y times z is working a similar way to x and y. So anyway, that's some insight to how quadratics work, but we'll do further clear examples in other videos. Sometimes the quadratics can actually show up by themselves and help you derive some of the vectors of the character table.